Okay, this is Building Useful Project Utils with Python. My name is Johan Herland. I work as a software engineer at Cisco in Norway. I work on some application level programming, but also do more underlying platform work, version control, build systems, developer tools, all the stuff that makes our main application run successfully on our software platform. For this talk, I'm going to assume that you have some basic familiarity with Unix shell scripting. Bash is the typical language used, but they're all very similar. And I'm also going to assume that you have some familiarity with Python 3. If your experience is mostly in Python 2, that also works. Some of these things are not available in Python 2. You can usually find alternatives there. But Python 3 is where the future of Python lies anyway, so that's what I'm going to concentrate on. So, I'm going to start with some motivation of this talk. What shell scripts are we talking about? What are shell scripts good for? Why is Python almost always better? Then I'm going to go through the conversion from a shell script to Python, some tips and techniques you could use, how to organize your code, how to write good command line interfaces in Python, how to run other programs from Python, because that's usually what you do from a shell script. How to manipulate the file system from Python, another common shell script thing. Also, I'm going to talk a little bit about writing unit tests in Python. That's typically not something you do in shell scripts, but that's one of the big advantages with moving to Python. You can start doing this. I have a slightly controversial take on error handling that I'll talk about, and then I'm going to move into a case study of a real-world shell script that I rewrote into Python at Cisco. And how I needed to do that, because I needed to add features that would have been impossible in shell, but just walking through the process. And then some summary and some room for questions at the end, hopefully. So, what kind of scripts are we talking about here? I sort of informally termed this the glue that holds your project together. If you go into your code base, you'll almost always find a bunch of shell scripts lying around everywhere. There might be developer tools, so like you have some complex command that is part of your workflow, and instead of remembering the whole command, you basically just put that into a shell script and you just run a shell script instead. So this could be for like running profiling or just helping you with deploying your changes through the build process onto your embedded product or whatever you're making. Shell scripts are often used at build time as well. If you have a very simple project, maybe your whole build system is a shell script, but generally you have a more complex build system, and if you say auto-generate code or you need some kind of helper for some part of your build system, that might be implemented in the shell script. People often use shell scripts for packaging, deployment, and release, publishing your assets to some server where they're available to your customer, signing release images if you're doing that kind of things. And at the end, in production, your customer, like if you're shipping a product, that product itself might have shell scripts running on it. So shell scripts basically running in at your customer site as well. So shell scripts, like we use them all the time, so they must be good for something. Well, they are really good for short and simple stuff. If your logic is straightforward and you don't have any data structures, yes, a shell script is a really good solution. It helps you to take, say, a complex command or a few commands and wrap them into a nice little wrapper, and you don't have to remember all the stuff inside. But once shell script starts growing, if you add more and more logic to them, if you need some data structures in there, if you need some configurability, say from the command line, and if you start refactoring things into functions to make them reusable, yeah, it supports some of that, but it quickly becomes a horrible mess, basically. If you open a shell script and it's longer than a screen full of text, it takes quite a bit of motivation to actually get into it and understand what it does, because it has quite a esoteric syntax sometimes. And also, as your shell scripts grow, you'll run into safety problems pretty soon. You have to be very disciplined as a shell script programmer to write safe shell script code. I'll look at some more examples here soon. So, why is Python any better? So I'm just going to do a quick comparison between shell and Python. So for shell, you have a fairly easy syntax. It's very similar to what you know from the command line work. So if you're used to working on the command line, those skills are very transferable into a shell script because it's basically just commands, one command after another one. So it's easy to become productive. But the complexity, like once you write more and more complex shell scripts, they basically become write-only scripts. It's really, really hard to read them. You write them once, and then if you have to make changes, that's hard. But shell has one thing going for it. It's trivial to run other programs from shell, and that's basically how shell scripts are. The whole reason for shell scripts, because shell itself is a very, very minimal language. You don't have much in terms of utilities available in the language itself. It's all about running your other system utilities to get stuff done. It's fairly or reasonably easy to learn shell because you can search online and you can find lots of resources and examples. But a lot of the shell scripts you find online are not always of any good quality. And here is my favorite sort of safety feature. There are more safety problems in shell, but this is the most common one. So we have this file name variable, and we set it to this file name, and then we try to touch that file name. Well, what you'll actually end up here is you're going to touch three files. You're going to touch one file called my, another file called favorite, and a third file called quotations.txt, because this is what shell does. Shell don't do types of variables and string handling very well, especially once you move out of the scope of 8-character long file names without spaces, and yeah, like there are lots of pitfalls in shell scripts. On the other hand, Python has a very simple and beginner-friendly syntax. The learning curve for Python is fairly shallow in that you can get productive quickly with a very small subset of the language. Lots of people consider Python one of the most readable languages. It's not as trivial to run other programs from Python as it is from shell, but it's fairly easy, and I'm going to walk through some of those ways. It definitely has fewer pitfalls than shell. You don't have to worry about this. Strings are treated in this way, and you have to keep that in mind when you write these scripts. There's lots of literature and resources online to learn Python, and when you find a Python example, like Python has a fairly good, consistent style to it. And the examples you find online are usually, in my opinion at least, or in my experience, they are of better quality than the example shell scripts you find online. Data structures and types. So in shell, everything is a string. Whitespace, as I said, in values often cause problems, and you must be very careful when dealing with variables and their values in shell. There is some support for integer arithmetic and some support for arrays, especially if you move into the more advanced shell scripting languages like Bash. But if you want to stay to a common subset, there are very limited things you can do. And I found this quote from the Advanced Bash Scripting Guide, which I think is gold. Unlike many, and especially at a conference like this, where there is lots of C++ and lots of high-level talks about advanced types and how to basically build good type systems, this is so different. Unlike many other programming languages, Bash does not segregate its variables by type. Essentially, Bash variables are character strings, but depending on context, Bash permits arithmetic operations and comparisons on variables. The determining factor is whether the value of a variable contains only digits. So that's a fairly fresh take on the whole concept of types when you come from something like C++, for example. Python, on the other hand, it's very dynamically typed in that a variable doesn't, you don't specify the type of a variable and it has to stay that way. You do have type annotations in modern Python, but I'm not going to cover that here. It's dynamically typed, but it's also strongly typed. When Python has determined the type of variable, Python is fairly strict about handling that type. It's not like integers suddenly turn into strings, or strings turn into integers, or you can concatenate a floating point value with a string like you can in JavaScript, for example. And I find this a fairly good balance in Python. It allows you to do a lot of things very easily, but still Python will prevent you from doing a lot of easy mistakes that you can do when you have a weakly typed language. You have a fair amount of built-in types. You have the usual numerics in float and complex. You have sequences. You have lists and tuples and ranges. You have text and binary data. Sets and dict, which is the mapping type, dictionary. And then you have other types as well. Basically, in Python, everything is an object. So even your modules that you write in Python, your classes, class instances, functions, methods, exceptions, everything is an object. And it's very dynamic. You can introspect through the language and look up, say, I imported this module. I can now loop through the various functions available from that module, for example. Modularity. So when you write a shell, you can structure your shell scripts with functions. The scoping behavior of functions in shell scripts are not always obvious. There are some weird rules where variables are global by default, for example. So if you run a function and it modifies a variable internally, that might actually modify some global variable, and you might not expect that, depending on how much experience you have with shell scripts. If you're talking about modularity between files, basically putting your code into different shell scripts and accessing it, you can access it in two ways. You can either, from one shell script, directly invoke another shell script as basically as a separate process. Or you can use the source statement, or in some dialects, basically simply a dot. So when you just call a shell script, you basically run it as a separate process. But when you use the source, you can think of that as a hash include. Basically, the source of that shell script is run within the context of your shell script. So if that sets up a variable, you can now access that variable from your script. But if you write a script to be sourced by another script, well, a script cannot easily figure out whether it has been sourced by a different script or whether it was just called from the command line or called from somewhere else. So typically, when you write a script, you either write it as a list of instructions to be performed, and there might be some functions for refactoring your functionality out of there, or you write it simply as a bag of functions that if you just run it, it does nothing except declare those functions and maybe some variables. And it's basically intended just for being sourced by other shell scripts, which then contain your main functionality. In Python, so within a Python file, you can structure your code into functions, but you also have classes and you have proper data structures. So this allows you to basically factor your code into a form that is most suitable for what you're trying to express. Between files, you can access Python files in two ways. I basically put import first here because that's what you're going to do the most often. So import, you could think of that as like source in shell, in that your Python program gets direct access to a different Python file. But it has proper namespaces. So if I source a shell script here from some other shell script, and it declares a variable foo, that variable foo is now directly in my namespace. There is no concept of separate namespaces. But in Python, if I import a module, then the stuff in that module is accessible to me by default via that module's name, dot something. So that's sort of separated into its own namespace. It doesn't pollute my namespace. I can also call another Python script via a subprocess to basically call it as a regular process. That's typically not what you do between Python programs, though. And one small detail I'm going to cover later here is if you have a main guard, and I'm going to show you what that is, that allows for a Python script to detect whether it's run directly or whether it was imported from some other module. And this allows a Python file to be written both as a script that can be run from the command line and as a module that can be imported from other Python code. And this is quite a useful concept. So, here's a shell script, foo.sh. It basically starts out by echoing this to the screen. This is always run, and then it declares a function that does another echo. So yeah, if I just run foo.sh, it's going to do that, and it's going to declare this function, but it's not going to run that function. I'm not calling this function, so this will not show up if you just run foo.sh. And then you have bar.sh. This one sources foo, and then it runs that function. So in both cases, well, when I run foo, this one is going to be printed. But when I run bar, this one is going to be printed, and then I call foo, and I'm going to print this one. So this statement is always run. And there's no easy way in shell for foo to basically detect that, I'm being sourced, so I don't want to do this, or now I'm being run, so now I want to do my main logic. Whereas in Python, so this is fairly similar code, Python basically says, okay, I want to print this always, and then I declare this function foo that does a print as well. And I'm going to skip that for now. In bar, we import foo, and then we call foo.foo to invoke this function. So now, when I run bar, this import statement is actually going to run this code. And it's going to do the print. So this is always run. Even when you run bar, this is also printed. And then it declares a function. It doesn't run it yet. And then when it gets down here, it's going to say, if name equals main, which basically means, is foo the main script in this Python process? And if it's not, we're just going to skip this. So from when foo is run on its own, this is printed, and this is printed. But when you run bar, we import foo. This is printed, this is skipped, and basically you have this facility in Python for foo to detect that, I'm being imported, I don't need to run this. And then we do this call down here, and it's going to do the call to foo. So, more shell versus Python comparison. Tools and libraries. As I said, the shell script language itself is very minimal. You use system binaries from Unix or from elsewhere in your system to do the heavy lifting. In Python, Python is very different here. Python has a very, very rich standard library. You can do most things within the language without having to call out to external processes. Lots more third-party modules are available online. So if you want to get even more functionality, you can find that there. And you can use the subprocess module to call out to other binaries on your system. So you can still interact with other binaries, just like you depend on from shell scripts. It's slightly more fiddly from Python than from shell, though. So, converting a shell script to Python, some tips and techniques. First, just how to organize your code. As we saw earlier here, the Python script, you can have statements at the top level. If you're used to C and C++, you don't really have this. You can't, you need to put something in, you need to put your statements inside a function for them to actually work. You can't just have printf on the top level. But you can in Python, and you do in shell. So when converting from shell to Python, you can simply start by transcribing your shell script into Python. One statement after another, you don't need to change the structure at all. Everything is run from top to bottom in the same way in both languages. And then you can start refactoring your Python script, or your very shell-like Python script, with functions and classes and data structures, and you can sort of incrementally improve the structure of your script. And you can add the main guard, and this makes it possible for your Python script to be imported from another script. Because before this, so say you have a shell script and it does some stuff, like say it removes some file, or it moves some files around the file system. If you just rewrite that into Python, the Python script will do the same. When you run it, it'll just move some files around. But if you now imported that Python script from a different Python script, it would still just go ahead and move those files. And you probably don't want to do that when you import it from another script, because the reason to import it is to access some reusable functionality within your Python script. And that's why you add the main guard. Because now, if you protect the main execution of the script inside the main guard, all the other stuff becomes available without your script going around and doing the stuff every time it is imported. After you've added a main guard, typically you'll add a main function as well, just to sort of organize the main execution of your code into a separate function. This is a common convention in Python, but it's also another script can now import your script and then run its main to basically execute that script, instead of having to use subprocess run to basically execute it in a separate process. And as you move along, you can split reusable functionality into separate modules. You can start distributing your code over several Python scripts to make sure that each script does one thing, does it well, and has, basically make sure that your code is factored in a nice way. And at this point, you can start adding unit tests to verify the APIs of those reusable components. So, command line interfaces in Python. So a lot of shell scripts, they're there for you or someone to run from the command line. So command line interfaces is something you typically write in shell. I'm going to argue that writing a command line interface in Python is a much better experience than trying to do it properly in shell. First of all, you're running on Unix, you probably want to follow regular Unix conventions, like if your script exits with 0, that means success. If it exits non-zero, that means failure. Nice thing with Python is that if you just run some statements through Python and you don't have an explicit exit, it just falls off the end of the script, it's going to exit with 0. And if you throw an exception inside Python and it escapes and you get a traceback on the command line, it's also going to make sure the exit code is non-zero. So if you just write a Python script, you don't worry about exit codes. If it completes, it's going to exit 0. If it fails with some exceptions, it's going to exit with non-zero. That's a nice convention, or a nice default at least. One typical thing you do for a Unix or in the Unix convention is to use sysstandard in and sysstandard out for default I/O. So standard in and standard out are these conventions for getting your default input and where to write your default output. Print in Python defaults to standard out. So the defaults in Python are set up to work with this. If you use the logging module in Python, it's going to default to printing your log messages on standard error, which is the Unix convention for logging errors and warnings. And typically when you write your command line interfaces, how most Unix commands do this is that mandatory command line arguments are positional arguments. So say when you move a file from A to B, you don't have, the command is mv a b. So those are positional arguments, the first argument, the second argument. You don't use optional command line arguments to specify mandatory arguments. And I'll show you how basically doing this in Python is fairly simple. So the key here is the argparse module. This is part of the Python standard library, and it's what you want to use to write nice command line interfaces. So here's a fairly simple program. Let's just quickly go through what it does. So we have a string at the top declaring the intention of the program. We calculate the square of a given number. We have a helper function here called calc. It takes a number and an exponent, and it returns the number raised to that exponent. This is just an example to show, all simple, nothing magic going on here. And then we have a main function. We have some command line parsing here. I'll go through that. And basically, we have this main guard down here. So if the name of this module is dunder main, so double underscore main, or in Python lingo, dunder for double underscore main. If the script is run from the command line, basically, then we're going to call the main function. So at this point, we're going to do the main logic of the program. If I wrote a different Python script that imported this one, this would not hit. We wouldn't execute this. This one would still be available to my other script. So now I can import this script from a different script, and I can access the calc functionality without having to run the whole thing and without having to parse command line arguments or pass command line arguments to get this one to do the job I want from it. But let's assume we're running it from the command line. We end up in main here. So here we set up a command line parser. So first, the argument parser takes some description of your program. I'm basically assigning that from this docstring up here. And in Python, you can access that through looking up the modules that you have loaded, indexed by this name to get this module, and then the dunder doc is this docstring up here. That's sort of a nice convention. Like you can write a nice comment at the top of your program, and that's also going to be part of your usage message in the command line interface. I'm going to show you that. Then we add an argument. We add an argument called num. This is a type int, which basically means that when Python parses this command line argument, it's going to run it through the int function, which will basically turn the string into an integer. So we take basically the number to be squared. We take that as our first command line argument. Then we add an optional command line argument, --cube, or for short, -3. So you can basically have aliases for options here. And this, you're going to use this command line argument to calculate the cube instead of the square. So basically we have an option to modify the behavior of the program. This has an action of store true. Basically this means that cube is going to be a Boolean flag that's going to default to false. And if you actually specify cube on the command line, it's going to store true there instead. And then we're going to have another optional argument, file, which is basically where we want to write the result. And it's going to default to standard out. And I say this here, default equals this standard out. And this type argument here basically says that when you write the file name and the command line here, that file name is going to be passed to this thing, which is basically going to open that file for writing and give you the file object. So it's ready to be written to. But if you don't give anything, you're going to get sysstandard out, which is already a file object ready to be written to. So this is basically how you declare the whole command line interface. Then we tell the parser to parse our actual command line arguments, and you're going to get those back in args. And here we can now call calc with a number from the command line. So this num becomes args.num. And then if args.cube, so this is the Boolean which defaults to false, but if you actually pass this argument, it's going to be true. So basically, we're going to call calc with the number, and then we're going to call it with 3 if that cube argument was given, else we're going to call it with 2. So we're going to end up calling calc here with a number and the exponent, which is either 3 or 2. And the result comes back from calc, and we're just going to print that to the file, the args.file argument, which by default will be our standard output. So, yeah, this is pretty much exactly what I said, I think, yeah. So, if you just run this script from the command line, no arguments at all, it's going to complain. The following arguments are required, num. So you didn't specify a number, so this won't work. But it's going to print also a small usage message saying how to use the script. So basically you want to call the script, you can give an -h, a -cube, or a -file, but you have to give a num. Now, if you run it with -h, so this is sort of a magic or an implicit help option that the argparse module will give you. And it'll now give you a nicely formatted help for your command based on the command line interface we just defined. So it's going to say, calculate the square of a given number. The positional arguments you need to give is num, and that's the number to be squared, and you have some optional arguments here. You can pass -h or -help to get this message. You have the cube option with a help string, and the file option with a help string. So now if we call my script with 5, we're going to just get back the result, 25. Because basically this was printed to our standard output. That was the default option. If I give it -3, it's going to cube instead. So the cube of 5 is 125, obviously. And if I specify an output file, it's going to put the result into the file called foo. And then if I cat the file foo, I'm going to get the result. So that was argparse. Now let's look at how to run other programs from your Python scripts. Subprocess. So basically, you import the subprocess module, you prepare a command line. Here you want to prepare the command line typically as a list of strings. Python supports passing the whole command line as a single string as well, but then it needs to run it through the shell to get shell expansion and everything sort of properly decoded. So everybody advises or the advice is to basically pass a list of strings. This allows you to basically handle command line arguments with spaces in them properly. And then you basically call subprocess.run with this list, and that will run the subprocess. And you can get the you can use the return code attribute from that call to get the exit code. So that's how you run a command and get its exit code. If you want to run a command and raise an exception if it fails, so if it returns a non-zero exit code, then you basically just add check equals true to the run call, and you'll get an exception if it fails. So that's even easier than getting the exit code and then doing an if on the exit code. Sometimes you want to run a process to actually catch its output and put that into a string variable. So here's how you do that. Typically you can pass check equals true, so that you get an exception if the program fails, and capture output true will basically now give you a result object where you can extract the standard out and the standard error from that process. So there is this extra boilerplate of subprocess run and basically organizing your command into an array of strings instead of a simple string, but otherwise it's not much harder to run an external process in Python than it is from a shell script. There are lots of more complex cases for running external commands. You can set up pipes to the external process and pipe to a standard output, or get a pipe from a standard output and pipe from that process to a different process and stuff like that. All that is documented in the main Python documentation, and this is one of the nicer modules to read the documentation for. It's fairly straightforward. Manipulating the file system from Python. This is another thing that shell scripts often do. You move some files around, you create some directories, you do something with the file system from a shell script. So how do you do the same from Python? Well, in Python 3, around when Python 3 showed up, you also got the pathlib module. You can get this from Python 2, but it requires a separate download. But the pathlib module allows you a nice interface for manipulating paths, basically. So you can create, move, remove files and directories. You can look for specific types of files around the file system. It has a nice handling of relative versus absolute paths. In large part, it replaces or supersedes os.path functions and other OS parts of Python if you're used to those. And it also supersedes fnmatch for doing path pattern matching, like star.txt kind of matching, and also glob, which actually goes onto the file system and gets files that match a certain pattern. Proper documentation is there. I'm just gonna do a very simple example here. OS and OS path are still in Python, and there are stuff there that is not in pathlib, so you'll still might need to do these. There's also shutil, which contains more higher level shell functionality. But here's a simple pathlib example. So you start by, from pathlib, import path. There's some other stuff in pathlib, but typically path is the class you want. And then we can say my directory equals path.cwd, current working directory. So that's where your script is, the current directory for your script. Slash, so basically pathlib has overloaded the slash operator or division operator to basically do path concatenation. So here we're basically getting the mydir directory relative to the current directory. And then we create that directory. And if it already exists, well, that's fine. We're just going to keep going. If you don't pass the exist OK equals true, then mkdir will raise an exception if the directory exists. And then we're going to create a foo path, which is the foo.txt file inside that my directory. This just creates the path object. It doesn't actually create the file. And then if foo.exists, so if that file exists, we're going to rename it to foo.backup. Foo with suffix backup basically takes the last suffix of the file name and replaces it with the one you gave it there. And then with foo.open WSF, so basically we're going to open the foo file in writable mode. We're now going to iterate through my directory, so basically get all the files or all the paths within my directory. And then we're going to print that path relative to my directory into that file. So I'm basically just taking a directory listing of mydir and printing it into that foo.txt file. And then finally, I'm going to look up all the star.backup files inside my directory, and I'm going to unlink them. So I'm not quite sure what this program is meant to be doing, but it's a fairly nice example of what you can do with pathlib. Pretty much all we're doing here are methods on path objects. So a little bit about writing unit tests in Python. This is not a talk on test frameworks or unit testing in general. And typically, when your scripts grow, you'll typically put your tests into separate files. But I'm just going to show you some small tests that you put in the same file just to get started unit testing. You have lots of different test frameworks available. The most used is probably unit-test, but a lot of people don't like it. PyTest is probably a better one, and it's gaining popularity fast, but it's not in the standard library. And there's doctest, which is very nifty, and I'm going to actually show you doctest first. So remember this script. This is the squaring the numbers, everything. So I'm now going to basically add some unit tests to this script with each of the 3 methods. So for doctest, so if you just want to ad hoc test this script, you can just start the Python interpreter, so basically start the Python REPL. You can import my script, and you can run myscript.calc32. Basically, we want to square number 3, and we get the answer 9. So that's how you can sort of interrogate your script from the command line. Now let's formalize that just a tiny bit. So in calc, we add this doc string, which basically documents how documents the module. And typically in the doc string, you add a small message saying how to use this or what it does. But then let's just copy some stuff from the Python REPL into the doc string. So we're just going to pretend there is a Python doc string here. We're just going to type in the 3 chevrons, and then we're going to type in some expression, and we're going to type in the result we expect from this. So here we're basically making a list with 3 calls to calc. We're going to square 0, we're going to square 1, and we're going to square 2. And we're going to expect that this results in a list that contains the numbers 0, 1, and 4. And then we're going to do the same with cubing, and we're going to expect a list containing the values 0, 1, and 8. And we're basically just adding some documentation or some, a string into the calc function itself. And that's all the change we're going to do to our script. Now, from the command line, we can run python-m-doctest and then pass it myscript.py. We're just going to add a -v to get some verbose output as well. And this is now actually going to look through the doc string, look up the things that look like Python expressions from the REPL. It's going to execute them with this module loaded and expect those results that we expected here. And it's basically going to run calc with those arguments and make sure that we get that answer. So this is fairly magic, actually, but it's really nice to just get started doing some testing. You basically write, this is a couple of use cases for this function, and then you just run Python-m-doctest, and it's actually going to test those use cases. You can also run doctest from within the script itself. So in your main guard, you can just import doctest and then doctest.testmod for test this module. And it's going to do the same thing when you run the script from the command line. For unit test is a bit more clunky. You basically set up some classes, test case classes, and then they have some test methods that do stuff. So you can add this into the same file along with the rest of the stuff. You need to have an import unit test at the top to get access to the unit test case classes. But these are just classes that are declared. Nothing is going to be run automatically from your script. It's just going to be sort of dead code in your script. But you can run these tests from the command line by python-m-unittest on your script. And it's going to find these 6 tests and run them. You can also run the test from within the script. Like if you did not have a command line interface for this, you could instead have, when invoked from the command line, you basically call unittest.main instead. PyTest is a similar story, except that PyTest tests are often nicer and smaller to write. So here we just declare a function called test_calc, and the magic here is the name starts with test. That's what PyTest is going to recognize. We set up some test vectors. So basically, we're going to take 0 and square it, and we're going to expect 0. We're going to take 1 and square it and expect 1, 2 and square it and expect 4, and the same for the cube test cases. And then for the number and the exponent and our expected value in this list, we're going to assert that when we call calc with a number and an exponent, we get what we expect. So fairly simple example-based testing in 6 lines of code. You can run this from the command line. If you have pytest installed, you basically just do run pytest on your script, and it's going to find the tests and run them. And you can also import pytest from your script and run it like that. So, a slightly controversial take on error handling in Python scripts. And now I'm specific to Python scripts for system utilities, basically Python scripts that have replaced shell scripts. Don't. Often, when you write shell scripts or system utilities, these are scripts that don't necessarily receive the same care and attention that your main code base does. It's not where you do complete error handling. It's not where you care about all the cases. And often what you end up doing instead is you try to run some code, you catch some exceptions, and you basically just print an error message and exit. And instead of doing that, it's often better to have the Python exception just bubble out to the command line so that you can actually get the traceback in the on the command line. Part of the reason why I advocate this as well is that these Python scripts built as system utilities or as glue code in your project, the users of those scripts are often other developers. And it's often much quicker to basically get a Python traceback and directly sort of identify, okay, this is the part of the code that's failing, let's start looking at that, then actually get an error message and then trying to parse the code, figuring out, here's the error message, it was caused by that, and then start tracing and figuring out. And often what I find is that in that case, I need to remove that error message to get at the actual exception, see what actually failed, and then I can dig further and debug the script. So basically, sloppy error handling is worse than no error handling in Python because the Python tracebacks are really useful for debugging. And just simplify or remove error handling that might otherwise obscure the source of the error is basically what I advocate here. And yeah, allow the Python exceptions to escape and terminate the program. And that will also guarantee a non-zero exit code from your script, so it behaves like the Unix convention expects. Yeah. If there are simple usage or user errors in your script, say like you pass a wrong number of command line arguments and stuff like that, that is better handled with a simple error message, because trying to decode from a traceback that, I needed to pass 3 arguments is worse than the script simply saying, you need to pass 3 arguments. But as I showed you, argparse gives you this for free. When you use argparse, it's going to give you these error messages. Also, if your script is not actually run by other developers, if it's exposed to end users, for example, then that's a different story. Then I would argue that your script is actually part of your main code base. It's not a glue script, and these rules don't really apply anymore. So, a case study. I'm quickly running out of time, so I'm going to have to run through this fairly quickly. We build video conferencing systems. We have a build process. That build process creates a PKG file. You then use this script called binst to take that PKG file and push it onto a video conferencing hardware system to actually test your functionality. So this is a usual developer workflow. This is the shell script I started with. That's 450 lines of bash. It's not very pleasant. It has some helper functions, but the command line interface alone takes up about half the script. There is an almost data structure in that script that takes up about 30% of the script. There is some logic, but it ends up pretty much constructing this monster command line in the end. So basically, we're going to cat a file, which is the PKG file, and we're going to pass that over SSH to the endpoint, and we're going to invoke some stuff on the endpoint to make the endpoint actually, or the video conferencing system actually install that PKG. As I said, it's a complex script. How binst upgrades the conferencing system is different than how these conferencing systems are upgraded in the field. Binst pushes the PKG onto the system, whereas in the field, the system is told where to find the PKG, and then it pulls it. So, and also there's a new requirement on the script. We need to support systems that have multiple devices, and I'm going to talk about this here. So our conferencing endpoints, some of them are integrated in that you basically have the whole system in a single unit with an integrated camera. But you also have bigger systems, like here. This is just the camera. The main unit is there. Or in this case, the main unit is behind the screen, but it has 2 cameras that are actually separate devices from the main unit. And we call the main unit, we call it the codec. That's most of the historical name, I guess. So you have a codec and you have a separate camera, whereas here you have the codec and camera in one unit. Systems with multiple devices. So yeah, you basically, when you upgrade these multiple device systems, you need to upgrade both the codec and the peripherals in tandem. Otherwise, the communication link breaks because they're running different versions. So we introduce some loads files to basically make sure that when you basically define which PKJs are needed for the codec and the cameras for those to work together. So that's a simple text format where it basically tells, if you're this kind of codec, you need this PKG. If you're that kind of camera, you need that PKG, and so on. And now you're going to run one or more build commands and then run a single binst to update the codec and its peripherals. So instead of this former workflow, we're going to run multiple build commands to get multiple PKGs for all the parts of the system, so basically the codec and the camera. And then we're going to have a loads file that references those PKGs. And there's a signature going along with that loads file. And binst is now going to tell the system about this loads file. And the system will use that loads file to pull down the PKGs it needs. So I need to add stuff to binst to basically deal with the loads files. But first, and I also need to serve that loads file to the endpoint using HTTP. That's not going to be very easy from a shell script. So basically, how do we get there? I first needed to rewrite binst from Bash into Python, and then refactor to make it more readable, and then I can start adding new features. So basically, first part is, here are some aspects of the rewrite from shell into Python. So this is what I meant with an almost data structure. We have a for loop up here that goes through the target that you might want to push. And then we basically have a switch case on the different target names. So these are basically target names from our build system corresponding to different types of endpoints. And this is basically code. It's not a data structure in itself. It's not reusable as a data structure. It's code that's run directly inside the shell script. But in Python, I can actually create a nice dictionary, and I can have nice named fields. And this, when I import binst from somewhere else, I can actually interrogate this target structure and get the same information out of the script without running everything. Command line interfaces. There are a couple of helper functions in shell, and then you have this monstrosity, which keeps going for another 100 or so lines, which parses the different command line options. The corresponding structure in Python is a fair bit shorter. It's a fair bit more verbose maybe than this, but it has nice documentation for all the options and everything. And it's much nicer to use from the command line than the original. So the rewrite basically ended up cutting 19% of the lines from the shell script. The command line interface now takes less than 20% of the file, and the data structure takes about a third of the file. And at this point, I can start adding new features to the Python script. So here basically is a script for creating those loads files I talked about. Basically, the script itself is 240 lines of Python imported by binst, but you can also run it standalone to create loads files when you're debugging. And okay, what if I wanted to make a loads file that's sort of formed like this instead? Then you can just run the loads file script directly. And it has a nice command line interface, all documented with the same techniques that I just showed you. We need to sign those loads files. So here's a separate script, load sign. That's about 300 lines of Python, but it basically allows you to sign the loads files both for test deployments and for release deployments. Here is a Python script that basically allows you to serve a loads file and the PKGs from a directory to an endpoint over HTTP. And all of these are basically imported from binst, and this is the code that I had to add to binst to get that loads behavior added. So basically what we do here is we start a load server, which we got from loadster, and we tell, now we basically log into the endpoint and we tell it to find the loads file to upgrade from, and now the endpoint will actually pull the upgrade from our server instead of us pushing it directly onto the endpoint. Yeah. And that's pretty much all for the case study. So in summary, you can feel free to use shell scripts for the very simplest of tasks. Like 3 lines of shell script is simpler than 7 lines of Python. But as soon as things start growing, really consider rewriting, and I would argue rewrite into Python. When you get more complex logic, when you get data structures, everything is going to be much better in Python. Write your Python scripts so that they can both be imported from other scripts to reuse stuff, but also to run them directly from the command line, so you can have nice developer tools with nice options. Refactor mercilessly. That goes for any code base that you care about. Unit tests gives you the confidence to refactor, so that's important when you start growing. And these are the 3 modules I would argue most for using when you build these system utilities. And I'm going to end on this quote. The Unix philosophy: write programs that do one thing and do it well. Write programs to work together. Write programs to handle text streams, because that's the universal interface. Thanks you. No time for questions here, but you can find me in the hallway.